Good day and welcome to our lecture video on graph theory. I am Jerome P. Gallego and together with my groupmates Mr. Lenard Ric T. Claro, Mr. Christian Kim L. Reyes, and Miss Raya Gwyneth TICAR, we will be discussing chapter 10 or 7 on graph theory planar graphs. Of the various ways to represent a graph G, the most insightful and practical thing to do is through drawing. Diba, when we're asked to give us a representation of this graph G with this number of vertices, this number of edges following these properties, diba, ang atong ginabuhat is we draw this graph. And we've observed nga some of these graphs have their edges crossed, while some of these graphs have no edges crossing. Diba? Let's example C4 and K4. Clearly, C4 is a graph in which iyang edges walay ka-cross. While K4 is a graph, well, na mga edges nga nag-cross. Now, these mga properties, ang atong mga observations na observe, leads us to a question. Can a graph G be drawn in a plane without its edges crossing? Or specifically, pwede ba nato ma-draw ang K4 nga dili mag-cross ang ihang edges? Now, kanisiya, this chapter now explores a special type of graphs in which those drawings are possible. Kung aha posible nga pwede nato mo i-drawingon ang isa ka graph sa iyang another isomorphic nga graph in which walay edges nag-cross. And then, Euler's discoveries play a key role in this study. A polyhedron is a three-dimensional object whose boundary consists of polygonal plane surfaces. These surfaces are typically called faces of the polyhedron. The boundary of a face consists of edges and vertices of the polygon. In this setting, the total number of faces in the polyhedron is commonly denoted by F, the total number of edges by E, and the total number of vertices by V. The best-known polyhedra are the so-called platonic solids, which includes the tetrahedron, the hexahedron, the octahedron, the dodecahedron, and then the icosahedron. Now, these are all shown figures in figure 10.1. Okay, now let us consider a polyhedron, specifically a tetrahedron. So this is a tetrahedron. How many vertices does our tetrahedron have? Count na nato, no? This is one vertex, V1, another vertex, V2, another vertex, V3, and another vertex na V4. How many edges do we have? We have here 1, 2, 3, 4, 5, and then kani is 6. How many faces does our tetrahedron have? Now this is one face, 1. This is also another face, 2. Ang sa ubos, okay, this is a 3 dimension, 3. And then ang likod ani, which is 4. So now our tetrahedron have 4 vertices, 6 edges, and 4 faces. And the boundary of a face, now consider F1. Consider na to F1. Diba? This is one face. Nga na ko siya F1. Consider F1. Diba, the boundary of a face consists of edges and vertices. And clearly, ang boundary ni F1 kay naay edges o naay vertices. And so again, a polyhedron is a 3D object bounded by a polygonal face, and each face is surrounded by edges and vertices. The number of vertices we denote as capital V, the number of edges as capital E, and the number of faces as capital F have a special relationship. And this relationship was discovered by Euler during the 18th century. The Euler polyhedral formula: if a polyhedron has V vertices, E edges, and F faces, then V minus E plus F is equal to 2. This formula applies to all convex polyhedra. It was first communicated by Euler in a letter to Goldbach in 1750. Now, this identity explains the structural harmony of polyhedra and provides a foundational insight into planar graph theory. Now, let us take a look at our 5 Platonic solids. For example, our tetrahedron. Applying Euler's identity, we know that a tetrahedron has 4 vertices minus 6 edges plus 4 faces. Unlike sign subtract, this is negative 2 plus 4 is equal to 2. Again, unlike sign subtract, then this is 2 is equal to 2. Now, if you consider a cube, a cube has 8 vertices minus 12 edges plus 6 faces. Clearly, this is equal to 2. Each polyhedron can be converted into a map and then into a graph by inserting a vertex at each meeting point of the map. So consider our tetrahedron. If I am to make this into a map, I'll just draw it like this. Now this is a map of a tetrahedron. If I am to make this into a graph, I'll just have to insert a vertex at each meeting point. And now this is a graph of a tetrahedron. Now, the graphs obtained by the 5 Platonic solids are shown in figure 10.3. Now, we have the cube, the octahedron, the dodecahedron, and then the icosahedron. Definition: a graph G is called a planar graph if G can be drawn in the plane without any of its 2 edges crossing. Such drawing is also called an embedding of G in the plane. In this case, embedding is a plane embedding. A graph G that is already drawn in the plane in this manner is a plane graph. Consider the graph K4. Can K4 be drawn into a graph without its edges crossing? Yes. And it will in a form, possible form, like this. Instead of connecting an edge here to here, yung mag-crossing ng edge, I'll just create an edge outside. So, since K4 can be drawn into a graph that end without any of its edges crossing, then K4 is a planar graph. If posible siya i-drawing nga dili mag-cross ang iyang edge, then planar graph siya. Then, kani siya nga graph, kaning na-drawing na nato, nga without any of its edges crossing, this is what we call a plane graph. So, dali ra kaayo, no? To show nga a graph G is a planar graph, you just have to draw. Now, you just have to show nga pwede na nato siya drawing isa lang, bisan isa. Pwede na niyo siya mapakita. Drawing kag isa, nga pwede na siya drawing nun nga wala iyang edges nag-cross. Now, let us again consider C4, another graph. We have cycle 4. No? This is a cycle 4. Is cycle 4 a planar graph? Yes, and it is already a plane graph because it is already a graph G that is drawn nga walay edges nga nag-cross. Hence, every plane graph is planar. And every planar graph can be drawn into a plane graph. Now, in particular, all 5 groups of Platonic solids atong ganinang tetrahedron are planar. When points in a plane that corresponds to the vertices and edges of a plane graph G are removed from the plane, the resulting connecting pieces of the plane are called regions of G. And one of these regions is unbounded, and we call it the exterior region of G. To visualize, let's look at the example and figure 10.4, the boundaries and regions of a plane graph. Now, let us consider this graph H. Diba, how many faces or regions does our graph H have? Can you see? This is one region, denoted as R1. This is also another region, R2, or another face. This is also another face, R3. And then, can you see? This is also another face. And then, R4. Diba, if we remove this plane that corresponds to the appeal siyang vertices of edges, then mo ni siya yung mga connecting pieces. Diba, the connecting pieces are kani for R2, kani for R1, kani for R3, kanino for R4, and then kani tipo niya exterior. Now these are kaning naa siya mga regions. No, the graph has 5 regions, no, denoted by again R1, R2, R3, this is R4, and then R5. Clearly, R5 is the exterior region because this region is unbounded sa ato ang plane. R1, R2, R3, and R4 are bounded, no? Those are bounded regions sa ato ang graph G. For a region R in a plane graph G, the vertices and edges incident to R forms a subgraph of G called the boundary of R. Now let us consider G1, which is a K4 and also a planar graph. G2 is a plane graph of G1. How many regions do we have? We have 4 regions. No, R1, R2, R3, and then the exterior region na R4. Now, if we consider the boundary of R1, diba, the boundary of R1 includes the edges and vertices incident with R1. Diba, if we consider R1, ang mga edges and vertices na incident to it is kani, kani, and kani. And this forms kani, which is a subgraph of G2. Same if we consider R3, the boundaries of R3 include kani, 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 and kaning mga edges. So this is also a subgraph of G2. How about the boundary of R4? Unsa nga mga edges ang vertices nga incident with R4? Kanino ang sa gawas? Walay labot ni ang sa sulod. Now this is the boundary of R4. Theorem 10.1, the Euler identity. For every connected plane graph G of order n, size m, and having R regions, then the following equation holds. N minus m plus r is equal to 2. Let us consider a connected plane graph G2 having 4 vertices, 6 edges, and 4 regions. By following Euler's identity formula, n minus m plus r should equal to 2, where we have 4 minus 6 plus 4 is equal to 2. No? Unlike sign subtract, negative 2 plus 4 is equal to 2. 2 is equal to 2. Let us consider another connected plane graph, G4, with 5 vertices, 6 edges, and 3 regions. 5 minus 6 plus 3 is equal to 2. Then we have corollary 10.2. If G is a plane graph with n vertices, m edges, and r regions, then n minus m plus r is equal to 1 plus the kappa of G. Let us consider the graph G4 from figure 10.5. So we have here G4, diba, by corollary 10.2. n minus m plus r should equal to 1 plus the kappa of, or the component of g. Now recall that k of g is denotes the number of components of a graph g. So we have here how many vertices? 1, 2, 3, 4, 5. 5 minus how many edges? 1, 2, 3, 4, 5, 6. Plus how many regions? We have 1, 2, and 3. Plus equal to 1. Plus how many component does G4 have? This is just equal to 1. We know that this is 2. And 1 plus 1, that is 2. Hence, this is an example for corollary 10.2. How about, let's have G2. Recall the graph of G2 from 10.5. N minus m plus r should equal to 1 plus the component of G3. Yeah, G3. We know this is 2. 1, how many component does G2 have? Which is just 1. So 1 plus 1, that is equal to 2. An upper bound for the size of planar graphs. If G is a connected plane graph of order 4 or more, then the boundary of every region of G must contain at least 3 edges. Now this observation in respect with the other planar graph shows that its size cannot be too great. Hence we have theorem 10.3. If G is a planar graph, again a planar graph of order n greater than or equal to 3 and size m, then m should be less than or equal to 3n minus 6. Let us consider a planar graph. Again, this is a planar graph since we can draw this without its edges crossing. Now again, this is of order 4. So if sakto to no, order n greater than or equal to 3. So ano to no, dapat its size should be less than or equal to 3n minus 6. So dapat tanan planar graph, dapat ang iyang size should always be less than or equal to 3n minus 6. So how many size? Pila may size ani? 1, 2, 3, 4, 5, and 6. 6 is less than or equal to pila ka buok vertices. Ay, 1, 2, 3, 4. 3 times 4 minus 6. So 6 is less than or equal to 3 times 4. That is 12. No? 12 minus 6. So we have here 6 is indeed less than or equal to 6. For theorem 10.4, let us consider K5. We have here graph G. Now question, is K5 a planar or non-planar graph? Let's test if K5 is a non-planar graph. Ano to no? By theorem 10.4, if M is greater than 3n minus 6, then G is a non-planar graph. So clearly, for K5, we have here 10 edges. How many vertices? We have 5. So 3 times 5 minus 6. 10 is greater than, that is 15 minus 6, that is 10 is greater than 9. By theorem 10.4, we've shown that the graph G or K5 is a non-planar graph. Then we have here corollary. This is corollary 10.5. This is not a theorem. Every planar graph contains a vertex of degree 5 or less. You know, recall K4. No, K4 is a planar graph. And tinuod jud nga, every planar graph contains a degree of a vertex of degree 5 or less. So we have here, no, kung kaning a vertex, we know this is of 3, 3, 3, and 3. So this is an immediate consequence by theorem 10.4. We have here theorem 10.6. At least one face of every polyhedron is bounded by a k cycle for some k where k is greater than or equal to 3. So kani siya nga theorem just assures that every polyhedron has at least one triangular face or higher. So this just confirms that a polyhedra dili day pwede nga tanan faces sa polyhedra kay naay fewer than 3 sides. Let us example tetrahedron or polyhedron, a tetrahedron. Diba? If tetrahedron has 4 faces, let's consider one face of the tetrahedron. Diba, how many sides does a tetrahedron have? Kani siya nga face sa tetrahedron. Diba, kay tulo. This is also a 3 cycle. Diba? This face has a 3 cycle. So, ginapakita lang ani, nga again, tanan polyhedra, dili pwede sa mga polyhedra nga tanan faces niya kay less than sa tulo. So, less than 3. Dapat 3 cycle or above. 3 cycle or above. And tinuod man, sa tetrahedron, sa upat ka faces sa tetrahedron, these are 3 cycle. So, mga 3 cycle. Let's example sa cube. How many faces does a cube have? Diba? A cube has 6. 6 sabok faces sa cube. Which is a square. Diba? Isa ka face sa cube is also a square. That is K4. That is a 4 cycle. Diba? K is equal to 4. So, that is a 4 cycle. And let's have a dodecahedron. Diba? A dodecahedron, how many faces does a dodecahedron have? It has 12. Nasa 12 kabuk faces. And each face sa dodecahedron is a pentagon. And a pentagon is a 5 cycle. So, gipakita rani nga theorem nga tanan faces dapat sa polyhedra, dapat na isa nga at least 3 ang iyahang cycle. So we have here a definition. A regular polyhedron is a polyhedron whose faces are bounded by congruent regular polygons and whose polyhedral angles are congruent. So if naa kay polyhedron and then its faces, meaning lang sa congruent regular polygons, it has its faces of same lang size and shape, then equal pa gyud ang ilahang mga angles within. So meaning if tanan faces niya kay equal, then tawag na siya is regular nga polyhedron. So theorem 10.7, there are exactly 5 regular polyhedra. There are 5, 5 lang, exactly 5 ka regular polyhedra. Let's have an example sa atong tetrahedron. Diba? A tetrahedron is one of the 5 regular polyhedra. Regular siya nga polyhedron because if we consider one of its faces, and compare it to another na po sa iyang face, it has exactly the same size and shape and also have the same polyhedral angle. Kaya tungod same man sila, if mo ni siyang tuyukon, tanawon nimo siya, same siya, kaya tungod same siya, then indeed, a tetrahedron is a 5 regular polyhedron. So we have here corollary 10.8 and corollary 10.5 or the graphs K5 and K33. By corollary 10.8, the graph K5 is non-planar. So we already know that this is true. By earlier, we've shown by theorem 10.4 that the graph K5 is non-planar because, if it's ganito by theorem 10.4, if G is a graph with M greater than N minus N times 3 times N minus 6, then G is non-planar. And indeed, 10 is greater than 9. Hence, K5 is non-planar. So, gagamitan na nato siya theorem 10.4. How about for corollary 10.9? The graph K33, that is a bipartite nga graph. So, for this bipartite graph, we cannot use theorem 10.4. So, dili na to pwede gamiton si theorem 10.4 para ma-prove na to si K33 kay non-planar. Instead, we have to use the Euler's identity. Indeed, K33 is non-planar.
Yeah, hi everyone. Today let us proceed to 10.2 maximal planar graphs. Now by definition, a maximal planar graph is a planar graph G if the addition to G of any edge joining two non-adjacent vertices together results in a non-planar graph. Now let's take the fourth graph in figure 10.6 as an example. So here it is. Now dere kaning example ana pa sa 10.6 nga figure, this is a maximal planar graph. Huh? This is a maximal. Now how do we know if it is a maximal? Now if we try to identify the vertices that are adjacent, kani sila, as you may have noticed, this vertex and this vertex are non-adjacent. No? Now why do we consider the vertices nga less than n minus 1? So for this example, since ang n minus 1 is the highest degree that a vertex can have, mga, no? So if we have a vertex with degree n minus 1, buot pasabot ra na kay adjacent sa tanan nga other vertices, no? So that's why dili na siya i-consider kay adjacent man siya sa tanan. So that's why gi-exclude na to mga vertices with n minus 1 since mangita ta mga vertex nga non-adjacent sila. No? So here we have kani and kani. Incidentally, kuan mo sila non-adjacent. So by the definition, if we try to make them adjacent, no? Kani sila og kani mag-cross man siya, which will then make it a non-planar graph. Kasi nga no ganito, if we have an edge nga mag-cross sila, that would be a non-planar graph. So ang mga planar graph baya no kay katong mga graphs nga ilang edges kay dili mag-intersect or mag-cross. So that is why wala naman puilaing mga vertices nga adjacent no kanilang sila og kani sila kay 4 naman sila upat. So the other vertices na lang nga wala pa is this one and also this one. So that's why this graph is actually a maximal. No? That is why it is a maximal. That is why dito sa atong example, it states that it is one of the maximal planar graphs. Okay, now let's try another example. Now, in our previous example, we have only verified if it was actually a maximal planar graph. So, in this one, we have to actually find out the maximal planar graph of this specific graph. Huh? So, kung nabantayan nato, daghan pa kayo og mga vertices nga non-adjacent, no? Like, for example, kani siya, dili siya adjacent ani niya, no? Dili siya adjacent ani niya, and kanipod, no? Wala may edge nga nag-connect sila, ha? And also, kanipod. No? So, let's try and connect them, or let's make them adjacent, no? Kung mag-try ta og connect ana, no, dili siya mag-result into a non-planar graph kaya wala may mga edges nga nag-connect. So magpadayon ta. And kani butang na butang nga ana and bam. Okay. So how about other vertices po, no? So kani siya nga vertex pod kay dili siya adjacent ani and dili po siya adjacent ani and kani. Now let's try to connect them. So kani okay siya and kani okay no. So far walay mga edges nga nag-connect and walay mga edges nga nag-intersect, I mean, and walay nag-cross. So far it is still considered a planar graph. Magpadayon ta og himo og mga edges sa mga non-adjacent vertices, hantod mag-result siya og non-planar graph. So napabantay laing mga vertices diri nga non-adjacent ta. So far kay kanina lang og kani, no? Kani and also kani and kani. So if you may have noticed, no? Kung i-try nito siya og connect manggod, mag-cross siya diri adapita. And kani pod mag-cross po siya diri adapita, no? O kani og kani if we try to connect them with kani, no? Kana. So napabatay lain non-adjacent vertices. And by that, wala na dyan laing mga posibleng vertices nga pwede na ito ma-connect nga dili siya mag-result in a planar graph. So that's why this is now considered as a maximal. no? It is now a maximal planar graph since kung magdungag pa ta og mga edges sa ato ang graph, mag-result naman siya in non-planar graph. So that's why they're katataman. And so the most number of edges is more ni siya. So that's why it is a maximal. Oh, this is the maximal. And kani siya, it is the graph sa ato ang 10.6. No? We can kana. Huh? Actually, na-verify na to that this one is a maximal planar graph. Ato na to siya gipangkuhaan og kanina. Kani nga mga edges. And now we have verified that this is a maximal planar graph. And also in our drawing, di siya. Diba parehara? Now this is a maximal planar graph according to our article. No? So, if we have a maximal planar graph, it states here that necessarily then, if we have a maximal planar graph of n minus 3 and size m, this will result in our number of regions. Then the boundary of every region is the triangle, not the boundary now. And so it will follow that 3 times our regions, number of regions, is equal to twice our size. Okay. So let's take this as an example. No? Let's try to verify this information. So, kani siya, it has n is equal to 4 number of vertices, so greater than 3. Satisfy siya na, as you can see here. And it has m, pinakabuk iyahang edges, so 1, 2, 3, 4, 5, 6 kabuk ang iyahang number of edges. And the number of regions are, no, we have this one, this, and this. So a total of 4 regions. R is equal to 4. And it also states that the boundary of every region of G is a triangle. Now, the boundary of every region, for example, kani, ka region, di ba yung boundary kay kani siya? Oh. And incidentally, it is a triangle. And this one, napod tayong ani, triangle na. And also for this one. How about this one? What is the boundary of this? And as you may have noticed, kani siya. And by that, we have verified that every boundary of the region is a triangle. So this one, and these regions. Now, let us try to test if 3 times our number of regions is equal to twice our size. So we have 3r is equal to 2m. Now we have 3, the number of regions is 4, twice our size. Let's test. Diba? It is 12. So for order n daw, greater than or equal to 3, mo results daw siya of our number of regions, and every boundary of the region is a triangle, and mo follow that 3 times our number of regions is equal to twice our size. Huh? So we have seen here. So that is that. Okay, now that we have established the concept for maximal planar graphs, now let us move on to the concepts of nearly maximal planar graph. Now it states here that the definition is that a graph G is nearly maximal planar if there exists a planar embedding of G such that the boundary of every region of G is a cycle, at most of which is not a triangle. Now let us have an example for this nearly maximal planar graph. Now for this, figure 10.7, lahat doon sila kay nearly maximal planar graph. And as we have noticed, atong first example, this is actually the maximal planar graphs. No, so not the existence of a maximal planar graph that is also a nearly maximal planar graph. Now, nganong ingani man siya? So, as we have previously verified, kani siya kay maximal planar graph. And also, technically, mo satisfy po siya sa definition for our nearly maximal planar graph. Now, as you can see here, every region, napashow na to nga this is a triangle, kani siya. Also for this one, now for this region is a triangle, kani kay symmetric la. And of course here, triangle po siya. And also for our outer region, kani siya ang triangle, no? And again, it states here that at most one of which is not a triangle. So all of the cycles nga na-form sa atong mga boundaries sa atong mga regions is that less than or equal to 1. No, kaya na siya nga at most 1. So, nada existence nga isa nga dili siya triangle or less than. So, pwede tanan sila triangle or nay isa nga dili triangle. So, at this example, as we have shown earlier, tanan sila kay triangle, tanan cycles nga na-form na to are triangles. And by that, nag-satisfy gihapon sa atong definition. It is nearly a maximal planar graph and also a maximal planar graph as well. Now, how about the next example, kani siya? So, if we try to point out the regions, which is kani, kani, and also the outer regions, which is kani, no? Based on these regions, ato mga cycles nga ma-form, which are these, no? Mga boundaries ato mga regions, and also the outer one, which is kanino? Siya. So notice that every cycle, except sa atong outer cycle, no, is not a triangle. So tanan man sila triangle, but one of which is not a triangle. So walay walay duha nga dili triangle dira, at most one ra gyud, which is kaning outer. So that's why ni satisfy siya nga ang kaning B nato nga graph is nearly maximal planar graph. Now, so about this one, again, atong ipang point out, kani sila, kani. Notice that ang itong mga form dira kay triangle gyud sa tanan, no? Except again sa atong outer, which is kani, outer region, which is not a triangle. It satisfies nga it is nearly a maximal planar graph. So let us now continue to our discussion in theorem 10.10. So it states here that if G is a maximal planar graph of order n, so we have order n greater than or equal to 4, where the degree of every vertex of G is at least 3. So, buot pasabot ana, ang degree daw sa atong mga V is at least 3, at least meaning greater than or equal to 3 for all vertices sa ato ang graph G, which is a maximal planar graph by assumption, no? So let us try to verify this theorem, no? Mangita ta og maximal planar graph of order 4 or more. Kani siya, kay mga nearly maximal man so kada tong paggamiton. So ano siya dito nga n greater than or equal to 4. Mamili ta diri. So this graph satisfies nga it is of order greater than or equal to 4. So let us try if ang iyahang mga degrees is greater than or equal to 3. So kani siya nga degree, 3 siya. Kanipod kay 3 and also 3 and so on. No? So check para ani mo satisfy to ang theorem 10.10 na to. So how about for this one? It has 1, 2, 3, 4, and 5. So n is equal to 5, satisfying a greater than 4 or equal to 4. And also, iyang mga degrees kay greater than or equal to 3 ba? Kani kay 3, 4, 3, 4, and 4. So satisfy, no? And so on, mo-satisfy niya atong theorem 10.10 nga if we have a maximal planar graph G with order 4 or more, so sa mga degree gid ani nila jud tanan is that at least 3, no? When you say at least 3 greater than or equal to 3. Now let us proceed to theorem 10.11. So if our graph G is a maximal planar, so same pa rin, order 4 or more, then G contains at least one of the following. So first of which, a vertex of degree 3, na siya vertex at least isa nga degree 3, and also na siya a vertex of degree 4, or two adjacent vertices nga of degree 5. So naatay duha ka vertices, no? Ang degree daw ani kay 5 and also for the other one 5. And then kani siya two adjacent vertices, one of which has degree 5 and the other has degree 6, no? So ana pa siya diri kung ato ang maximal planar graph kay na siya order 4 or more, mag-contain siya at least 1 na gani, no? So dapat na isa nga mo satisfy diri, no? At least 1 lang gyud. No? Pwede po siya duha, pwede sa pairs, pwede sa kani or kani, pwede po siya sila, silang upat. So, maray ginaingon sa tong 10.11. So, okay, for theorem 10.12, if G is a maximal planar graph of order n greater than or equal to 4 and size m, now it will contain a vertices n sub I with degrees I, where I is greater than or equal to 3 but is less than or equal to the delta or the delta of G. Now, this maximal planar graph G will follow the distribution below, which is given by this equation. So 3n sub 1 plus 2n sub 4 plus n sub 5. Now this will be equal to 12 plus n sub 7 plus 2 n sub 8 plus and all the way to delta minus 6 n sub n. Now kaning mga n sub i's na to, which is n sub 3, n sub 4, and so on, muna ang katamang vertices with I degrees. So kaning sa n sub 3, so maning mga vertices nga with degree 3. And n sub 8, maning mga vertices with degree 8, and so on and so forth. Now let us remember this equation because we may need this later on. Now let's head on over to the concept of discharging, which is coined and introduced by Heinrich Hecht. Now the idea of assigning what is called a charge to each vertex of a planar graph, as well as discharging rules, which indicate how charges can be redistributed among the vertices. Let's now have a definition for the charge. Now it states here that in a maximal planar graph G, now each of these vertices would initially have a charge of positive 6 and would gradually decrease depending kung pila ka buok ang degrees nila. So for example, if our vertex has a degree of 2, so 6 minus 2 equals 4. No? So manandayon ang iyahang current charge dayon. Now in particular, every vertex of degree 5 receives a charge of positive 1, and every vertex of degree 6 receives a charge of 0. Ganaman, 6 minus the degree v, which is 6, 6 minus 6, may siyang 0, and of course, kung ma-exceed din siya 6, will have a negative charge. No? So, with degree 7 or more, mag-receive siya of negative charge. So, for example, to illustrate the idea of charges, now let's take this maximal planar graph, which is this one. Now, each of these vertices has initially, again, a charge of 6. Now, let us first identify pila ang mga vertices. Now, this one has 4. This one has 4 also, and this one has 3, 4, and 3. Now, with that, let us try to use the 6 minus the degree of v, which will identify their current charge. No? So now, this vertex has now a degree of 3. Now, because 6 minus 3 is 3, so it has a current charge of 3. And also, 6 minus 4 has a degree of currently 2. And of course, kani siya kay 3, 2, and so on and so forth. Now, these green markers that we have just wrote are the current charges for our vertices. No? So yes, yung lang ang idea sa charging and discharging. No? So matod pa kay Heinrich, magsugod ang each vertices og 6 and magagamay o magagamay ang charges sa usa ka vertex kung ingana apod kadaghan, kung unsa kadaghan ang iyahang degrees or pila ka buok adjacent edges sa iyaha. No? So basically, kato mga charges niya na 6 will distribute to each and every vertex nga iyahang adjacent. No? So mara na ang the gist of our concept here for the charging and discharging. In this idea, naka-introduce the charge na positive, neutral, which is 0, and of course, the negative. So with that concept in mind, let's proceed to theorem 10.13. Now it states here that if G is a maximal planar graph of order n greater than or equal to 4, now that with size m and with a maximum degree delta, capital delta of G, such that G has n sub I vertices of degree I. No? And now it will follow this equation. So for the summation of 6 minus I times n sub I, where I starts from 3 to capital delta. Now this is said to be just equal to positive 12. Now let us proceed to the corollary 10.14. Now it states here that if a G is a maximal planar again of order at least 4, greater than or equal to 4, then that G contains at least 4 vertices whose degrees are at most 5. So now, unsa may buot pasabot aning corollary nato, let us illustrate by using an example. So let us take the same example as we had last time, and also we'll add another one. Ano siya? So in our first graph, tara to kung masatisfy mo siya nga if n is greater than or equal to 4, na ay at least upat ka vertices, n number ka buok vertices, nga ihang degrees kay mo less than or equal to 5, since ano siya nga is 5. So we'll take 4. No? Suppose kani sila. No? So kani siya nga vertex, dili siya mula pa sa 5. Also kani di siya mula pa sa 5 because it is 4. Kani siya kay 3. Of course kani kay 4. No? So masatisfy gid siya nga at least upat sa ato maximal planar graph kay less than or equal to 5 bilhin niya mga degrees. Now how about for cycle 4? So ato ang base case no, n is equal to 4. How about for example n is equal to 4? No? So ang upat daw sa ilaha less than or equal to 4, at least natin upat. No? Less than or so ang upat daw sila at least upat kay less than or equal to 5. So as you may have seen, kani siya kay 3, kani siya kay 3, of course kani 3, 3. So natin at least upat, syempre upat siya kabuk vertex nga less than ang ilahang degree sa 5. So masatisfy yun ang ato ang corollary. So yung lang kasimple ang gina-state sa corollary, no? Whenever we have a maximal planar graph na greater than or equal to 4, so natin at least upat ka vertices with degrees less than or equal to 5. Okay. So how about the next one? We have a theorem 10.6. So if you have uptick ang mga mata, kaning theorem 10.6 kay similar lang ni siya atong previous na to, which is kanina theorem 10.11, no? As you have noticed, diba? Same lang. Figure 6. So ang kalahian lang ani nila kay nagamit siya og concept sa sa charging and discharging sa pag-prove. And some of you may have seen nga wala po tayo theorem 10.15 because actually same exact ra gyud sa 10.11 and also gigamitan na siya og concept sa charging and discharging proof. So unlike aning 10.11 lahi iyang method for proofs. So the theorem 10.15 show ran niya using the concepts of charging and discharging. So yan niya pag-prove. Now, for the last and final theorem for our maximal planar graphs, we have theorem 10.16. Now it states that if G is a maximal planar graph of order 4, so greater than or 4, then G contains at least one again of the following. So if ato ang maximal graph kana siya 4, order 4 or more, kada siya makuha nga at least aning tulo na ay vertex na degree of 3, other kana vertex of degree 4 or a vertex of degree 5 that is adjacent to two vertices, each of which has degree 5 or 6. So similar na kaya itong 10.11 and 10.15. So that is that. Thank you so much for listening. I may head on over to Raya. Raya?
So good day everyone. We will be reporting characteristics of planar graph. So under this anti-characteristic theorem, but first let us define subdivision. A graph H is a subdivision of a graph G if either H is isomorphic to G, or H can be obtained from G by inserting vertices of degree 2 into some of or none of the edges of G. So um, to further visualize that example from figure 10.9, so as you can see, atong graph H sub 1 is isomorphic sa atong G. So meaning atong H sub 1 is subdivision sa atong G. And then atong H sub 2 is subdivision siya sa atong H sub 1. Kaya as you can see, na-insert ta og vertices of degree 2 into some of the edges sa H sub 1. So meaning H sub 2 is subdivision sa atong H sub 1. And then, maupod sa H sub 3, add po ta og mga vertices of degree 2 from our H sub 2 mao naka-create ta og more paths. So, certainly, a subdivision H, a graph G, is planar if and only if G is planar. So, planar means makadraw ka sa iya sa plane without edge crossing. So, wala may edge na nag-cross sa G. So, meaning, atong G is planar. So, yung subdivision is also planar. Theorem 10.17. A graph G is planar only if G contains no subgraph that is a subdivision of complete graph K5 or complete tripartite graph K sub 33. So, itong K5 ug atong K sub 33 are non-planar graphs kay nag-contain na sila og mga edge crossing. So, if ato na silang i-subdivide and then ang ilahang subdivision is uh, na-contain sa graph G. So, meaning atong graph G is dili na planar. So, atong theorem is tinuod. A graph G is planar only if G dili siya mag-contain sa subdivision sa katong duha ka ng planar which is K5 or K sub 33. So, let's go to our main theorem which is Kuratowski's theorem. A graph G is planar if and only if G contains no subgraph that is a subdivision of K5 or K sub 33. So, pag-prove ani is two ways. So first is i-assume nato nga atong G is planar. So if i-subdivide nato atong G, dili maapektuhan iyang planarity. So since atong K5 o K sub 33 are non-planar, so atong G is dapat dili siya mag-contain og subgraphs or subdivision sa K5 or K sub 33 tungod kay mahimo atong G as non-planar. So next is i-assume nato nga atong G does not contain a subdivision of K5 or K sub 33. So, kailangan natin i-prove na itong G is planar. So, suppose atong G kay non-planar. So, by Kuratowski's characterization, G must contain a subdivision of K5 or K sub 33 which is contradiction. So, meaning itong G is planar. So, next is minors of graphs. If two adjacent vertices U and V in a graph G are identified, then we say that we have contracted the edge UV, denoting the result vertex by U or V. So for example, from our figure 10.13, atong graph G prime is obtained by contracting the edge UV in G. So ang mabili na lang nga vertex is either U or V. So in this case, ang mabili is gidenote niya as U. And then ato ang G double prime is obtained by contracting the edge WY in G prime. So ang nabili na lang is ang vertex W. So edge contraction simplify a graph G by merging two adjacent vertices into one, resulting in a smaller graph. A graph H obtained through a sequence of edge contractions can be described by a partition of V of G into subsets V1 up to V sub k. So for example, in the graph G of figure 10.13, if we were to let V sub 1 equal to T, V sub 2 is equal to UV, V sub 3 is equal to X, and V sub 4 is equal to WY, then the resulting graph H is shown in figure 10.14. So as you can see, same lang siya sa ato ang G double prime na graph of figure 10.13. This is obtained by successively contracting the edge UV in G and then the edge WY in G prime. Next, a graph H is called a minor of a graph G if either H is isomorphic to G, or a graph isomorphic to H can be obtained from G by a succession of edge contractions, edge deletions, and vertex deletions in any order. Equivalently, H is a minor of G if H is isomorphic to G, or H can be obtained from a subgraph of G by a succession of edge contractions. Consequently, a graph G is a minor of itself. If H is a minor of G such that H is not isomorphic to G, then H is called a proper minor of G. Now, a planar graph H of figure 10.14 is a minor of the planar graph G of that figure. So, every minor of a planar graph is planar. Then, the graph H sub 1 of figure 10.15 can be obtained from G sub 1 by successive edge contractions. So, for example, from G sub 1, if atong i-contract ang T sub 1 of T sub 2 will result to V sub 1 sa ato ang graph H sub 1. Then if i-contract na to from G sub 1 again, ang U sub 1 up to U sub 4 will result sa V sub 2 sa atong graph H. And then if i-contract na to ang V sub 1 from a graph G will result to V sub 3 from graph H. And if i-contract na to W sub 1 up to W sub 3 from graph G will result to V sub 4 sa graph H sub 1. And then i-contract ang X sub 1, X sub 2 sa graph G will result to V sub 5 sa graph H sub 1. Then if i-contract ang Y sub 1 sa graph G sub 1 will result to V sub 6. And then if i-contract ang Z sub 1 sa graph G sub 1 will result to V sub 7 sa ato ang graph H sub 1. So, H sub 1 is a minor of G sub 1. Now, by deleting the edge V sub 2, V sub 6, and the vertices V sub 6 and V sub 7, we see that we can form a graph of K5. It's also a minor of G sub 1.
Theorem 10.19. If a graph G is a subdivision of a graph H, then H is a minor of G. So for example, let H be a triangle with complete graph K sub 3 with vertices U, V, and W, and edges UV, VW, and WU. Now let G be a subdivision of H obtained by replacing each edge of H with a path. So replace UV with the path UXV, replace VW with the path VYW, replace WU with the path WZU. So this is a subdivision of H as each edge of H has been replaced by a path. So showing H is a minor of G, so to obtain H as a minor of G, contract the paths back into single edges. So contract UXV into the edge UV, contract VYW into the edge VW, contract WZU into the edge WU. After these contractions, the resulting graph is H is equal to K sub 3. So this demonstrates that H, the original graph, is a minor of G, its subdivision. Next is Theorem 10.20. If G is a non-planar graph, then K sub 5 or K sub 3 is a minor of G. So for example, let G be the complete graph on 6 vertices, or K sub 6. So this graph has every possible edge between its vertices. So ato i-show nga G is non-planar. So according to Krotowski's theorem, a graph G is non-planar if it contains K sub 5 or K sub 3. So since K sub 6 is highly connected, then it is non-planar. To obtain K5 as a minor of K sub 6, mag-delete ta o isa ka vertex, which is V sub 6, and all its incident edges from K sub 6. So which results sa atong graph nga K sub 5 na lang. So since K sub 5 is a minor of K sub 6 and K sub 5 is non-planar, this proves nga K sub 5 is a minor of G. Now, alternatively, to find K sub 3 as a minor, ato i-divide atong vertex set nga katong K sub 6 into two groups. So, natay A as V sub 1, V sub 2, V sub 3, and B, V sub 4, V sub 5, V sub 6. So, if mag-remove tag edges within A or within B, this will result now sa atong graph nga bipartite K sub 3, which iyang isa ka part is V1, V sub 2, V sub 3, and ang other part kay V sub 4, V sub 5, and V sub 6. So, K sub 6 is a non-planar graph. So, both K sub 5 and K sub 3 are minors of K sub 6, satisfying the statement nga If G is non-planar, then it contains K sub 5 or K sub 3 as a minor.
And now let's move on for our next topic now. The German mathematician Klaus Wagner shows that the converse of theorem 10.20 is true in 1937, only a year after obtaining his PhD, thereby giving another characterization of the planar graphs. So the theorem 10.21, which is the Wagner's theorem, state that the graph G is a planar if and only if neither key 5 nor key 33 is a minor of G. For the example, we had graph G, this one. So if we remove this isolated vertex, the edges, and this one, we remove that. So we form this H graph, which is a minor of this graph. So as what we can see, this graph doesn't contain any key 5 or key 3 minor. So this graph is a planar graph. So let's move on for the another example. So if we have this one, so I think we are familiar with this one. This is a Peterson graph. So if we create a minor of this graph, so if we construct the edge of connecting the inner and the outer vertices, then we get a key 5 minor of G. So this one, if we contract edges from the inner and the outer vertices, so the Peterson graph is not a planar graph. So that's all. Theorem 10.22 state that let G be a graph, and if G has a key 33 as a minor, then G contains a subdivision of the key 33. And if G has a key 5 as a minor, then G contains either a subdivision of key 5 or a subdivision of the key 33. In addition, also that all subdivision is a minor, but not all minor are subdivision. And that's all for this theorem. Our next topic now, it is the outer planar graph. So we now turn our attention to a special class of the planar graphs. A graph G is an outer planar if there exists a planar embedding of the G, so that every vertex of G lies on the boundary of the interextension or the region. And actually, if there is a planar embedding of G so that every vertex of G lies on the boundary of the same region of G, then G is an outer planar. Then the following two results provide the characterization of the outer planar graph. So for example, this is an example of the outer planar graphs because every single vertex is touching the infinite face. So that's this one is an example also of outer planar, but this one is a more complicated. But we can see that every single vertex is touching the infinite face. So let's give another example. This one. So this one is clearly not a outer planar because there are vertices that not touching the infinite face, but it can be embedded such that this graph is isomorphic to this one. So in this case, this one is an outer planar example because from this one not by embedding the other one which is isomorphic to this one, so we can conclude that this one is an outer planar graph. Theorem 10.23. A graph G is an outer planar if and only if the join G and VQ1 is planar. As an example for the theorem 10.23, no? So let G be a P4. So we know what is the P4 graph, no? This one, that which is an outer planar since all the vertices can be embedded on the outer face in the planar drawing. So in a definition, by adding a vertex, this is a vertex Q1, and connect it all to the vertices of the G, which is the P4, then the result is the graph is planar, satisfying the theorem 2.3. So that's the example of this theorem. The theorem 10.24 states that the graph G is outer planar if and only if G contains no subgraph that is a subdivision of key 4 or key 2 3. So here's the key 4 and the key 2 3 mentioned in the theorem 2.24. This one and this one. So let's have an example for the theorem. So if we have this graph, add by the another vertex, this one, the graph is still an outer planar graph because this graph doesn't have a subgraph that contains a subdivision of the key 4 and the key 2 3 that I've shown earlier. So this graph is an outer planar graph. So if this one, this is another example. This graph is a outer planar, if we add a vertex E here in the middle and making a subdivision of K4, so clearly this graph is not an outer planar because this graph making a subdivision of a K4 where an additional vertex E, this one, subdivides of the sum edges, making a graph a non-outer planar graph that violates the theorem 2.24. So that's all for this theorem. The theorem 10.25 states that every non-trivial outer planar graph contains at least two vertices of degree 2 or less. And the theorem 10.26 states that the size of every outer planar graph of order n is greater than or equal to 2 is at most 2n minus 3. So I'm gonna show you an example to illustrate these two theorems. Here's the illustration for the theorem 10.25 that say that every non-trivial outer planar graph contains at least two vertices of degree 2. So this one is an outer planar graph, which is a non-trivial graph. So this graph contains at least two vertices of degree 2. So this one and this one satisfy the theorem 10.25. So let's move on from the 10.25 and we use this graph for the example of the theorem 10.26 that says that the size of every outer planar graph of order n is greater than or equal to 2 is at most 2n minus 3. So we count the order. This graph is order 4. So 1, 2, 3, 4. So 4 is greater than 2. And the size of this graph is 2n, at most 2n minus 3. So Rn is 4. So 2 times 4 minus 3. So 8 minus 3. 8 minus 3 is equal to 5. So we count the size or the edges if this graph satisfy the theorem 10.26. So 1, 2, 3, 4, 5. So this graph satisfy that theorem 10.26, and this one is the illustration of 10.26. So that's all for this theorem.